The Webb look is so far out that getting light has been traveling for north of 13 billion years. Yet, the universe has been broadening, and in this manner, the light has been reaching out for the most far-off universes we're recalling in time, almost to the huge explosion. The monstrosity of the universe could appear huge, yet every single piece of it began from what we insinuate as the peculiarity. At this point, this is the manner by which we could decipher the huge explosion speculation. At any rate, the James Webb Space Telescope, JWST, has uncovered huge secrets about the birth and advancement of the universe, leaving us puzzled. Esteemed physicist Brian Cox has broadcasted that the essential revelations made by the JWST may, in fact, reshape how we might interpret the universe in general. Go along with us as we jump into these new radiant disclosures that guarantee to change our perception. The James Webb Space Telescope, named after the recognized NASA leader James E. Webb, stands as a marvel in current cosmic examination. This telescope addresses an immense mechanical jump forward from its precursor, the Hubble Space Telescope, coming about in view of a helpful exertion between NASA, the European Space Agency, and the Canadian Space Agency. The JWST outperforms the capacities of its envoy. It uses cutting-edge technology and a plan optimized for focusing on the universe in exceptional detail. Not like the Hubble, the JWST conveys clear, furthermore, and sharp pictures of distant sublime bodies, working primarily in the infrared range. This fascinating part allows it to penetrate cosmic buildup and catch divine things that were, beforehand, hid away from our view. With its beast 6.5-meter primary mirror, made from 18 hexagonal areas, the JWST reduces the Hubble's reflector size. Positioned approximately 1.5 million kilometers away from Earth at the second Lagrange point, L2, it circles the Sun in a condition of concordance with Earth, guaranteeing a consistent and persistent perspective on the universe while investigating the far-off corners of the universe. It includes investigating light years, yet it too involves a sort of time travel. The JWST utilizes infrared instruments to take note of wonderful articles and occasions returning billions of years. The light discharged by these items, in view of the extending universe, goes through redshift, moving from the visible range to the infrared frequency or longer. Fortunately, the JWST can recognize infrared light transmitted by sublime bodies at outrageous distances, enabling scientists to study the presentation of stars, research vast framework improvement, and look at exoplanet environments. Its most recent notable discovery includes recognizing an endless mass of vast frameworks at the edge of the visible universe. This tracking down challenges the legitimacy of the hypothesis of how things became, inciting a reassessment of our key cosmological presumptions to better comprehend how we showed up. As of now, we ought to take a short outing through the history of space investigation. Early civilizations, like the Greeks and Chinese, established the groundwork for understanding planetary development by observing heavenly bodies. Newton's guidelines in the 17th century gave us speculative construction for space travel. During the 20th century, Edwin Hubble, a powerful cosmologist, made notable disclosures in cosmology and observational space science. His observations uncovered that distant nebulae were detached universes long past the Milky Way, changing our comprehension of the universe's size and extension. Hubble's law, laid out by him, showed that worlds farther away were moving away at higher rates, giving confirmation to the development of the universe. The post-World War II history of space investigation marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit. Yuri Gagarin's orbital outing in 1961 and the Apollo 11 moon landing in 1969 were urgent achievements. Fast forward to 1990, when the Hubble Space Telescope was sent off, giving outstanding clarity and dazzling insights into the universe. The journey from old perceptions to the innovative wonders of the James Webb Space Telescope grandstands the consistent improvement of how we could interpret the universe. It revealed the boundlessness of space and changed crucial considerations in space science. Take the Hubble Space Telescope, HST, for example. It snapped the well-known Pillars of Creation picture in the Eagle Nebula, uncovering a star nursery formed by enormous sections of gas and dust. Another huge achievement was the Hubble Deep Field, capturing an enormous number of galaxies in seemingly a void patch of space. The HST also dove into exoplanet atmospheres, pinpointing parts like water and organic molecules in far-off worlds, implying the possibility of livable zones beyond our solar system. Following the advancement of the nearest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These accomplishments solidified the Hubble Space Telescope's legacy as a foundation of modern cosmology, stunning the world with its incredible cosmic revelations. Its substitution, the James Webb Space Telescope, was sent off to develop the innovative advancements and lessons gained from a model of our understanding of the universe's beginnings, which today is explained by the winning theory of the universe's origin around 13.8 billion years ago. The universe began as a hot and dense singularity, rapidly expanding and leading to matter, energy, and basic forces. As the universe expanded, it cooled, prompting the formation of particles, stars, galaxies, and the various structures observed today. The theory of how things came to be also explains cosmic microwave background radiation, light component overflow, and the large-scale structure of the universe. Regardless of being widely accepted now, the theory of the universe's origin faced wariness and challenges in its early days. Alternative models like the steady-state theory proposed the universe without a specific start. Additionally, concerns about evidence supporting the singularity's development and observed inconsistencies emerged. Most of these complaints were addressed over time, and a significant portion of evidence came with the detection of cosmic microwave background radiation in 1965, lining up with Big Bang predictions. Space missions like COBE and WMAP, along with technological advancements, further supported the theory. Precise measurements of cosmic microwave background radiation matched strikingly well with theoretical forecasts. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can glance through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light in the universe and observes objects formed soon after the Big Bang. Its infrared capabilities allow it to focus on star-forming areas, heavenly nurseries, and the development of stars hidden from optical telescopes. Infrared light, with longer frequencies compared to visible light, can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects emitting predominantly in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and far-off galaxies. As celestial bodies move away, their emitted light waves get extended, causing a shift toward longer frequencies, redshift. The JWST's infrared abilities can identify these. The JWST, by contrast, excels in these areas. With its ability to observe in the infrared, it provides a clearer view into regions that were once hidden from our sight. This opens up entirely new avenues of exploration in understanding the universe's earliest stages, particularly in the context of galaxy formation, star birth, and planetary system development. As the JWST peeks deeper into the cosmos, it is poised to reveal the unseen, the hidden, and the mysterious. One of the most significant breakthroughs expected from the JWST is the study of the very first galaxies that formed in the wake of the Big Bang. These galaxies, created just a few 100 million years after the event, are pivotal to understanding the rapid evolution of the universe. The JWST will be able to capture the faint signals of these galaxies, allowing scientists to observe their properties, shapes, and characteristics as they existed during the early stages of the universe's formation. Moreover, the JWST's ability to observe galaxies at various stages of their evolution allows astronomers to trace how galaxies have grown and changed over time. By studying the light from these distant objects, we gain valuable insights into the processes that shape galaxies, including the role of dark matter, the behavior of supermassive black holes at the centers of galaxies, and the mechanisms of star formation and death. Exoplanet exploration also remains a major focus for the JWST. With its advanced infrared capabilities, the telescope will be able to examine the atmospheres of exoplanets in far-off solar systems, identifying key components such as water vapor, methane, and other molecules. These findings are crucial for determining whether these exoplanets may harbor conditions suitable for life. By studying the atmospheres of these distant worlds, the JWST could offer clues as to whether or not life exists elsewhere in the universe, a question that has intrigued scientists for generations. Furthermore, the JWST will help to refine our understanding of the universe's large-scale structure and the forces that govern its expansion. Its observations of galaxy clusters and the distribution of dark matter will shed light on the fundamental forces driving the universe's evolution. It could also provide new insights into the mysterious phenomena of dark energy, which is believed to be responsible for the accelerated expansion of the universe. In summary, the James Webb Space Telescope represents a monumental leap forward in our exploration of the cosmos. By focusing on the infrared spectrum, it enables us to peer into the deepest recesses of space and time, revealing a universe that was previously hidden. From studying the birth of galaxies and stars to investigating the potential for life on distant exoplanets, the JWST promises to answer some of the most profound questions about the universe's past, present, and future. Residue and gas. The James Webb Space Telescope addresses a huge jump forward in noticing universes from the universe's beginning phases. Not at all like its ancestors, the JWST can notice heavenly items that formed within a scant few hundred million years after the Big Bang, utilizing its infrared responsiveness and high-level imaging capacities. The JWST has uncovered an overflow of old cosmic systems, offering striking clarity and detail in figuring out the universe's developmental history. Fundamental outcomes from JWST perceptions have mixed waves in laid-out cosmological models. The detailed data challenges some parts of winning hypotheses, inciting cosmologists to rethink essential standards overseeing how we comprehend vast advancement and construction. Errors between noticed information and hypothetical forecasts have started serious discussions inside the logical community. JWST perceptions have uncovered a larger number of systems in the early universe than expected by existing models, proposing a more perplexing and quick advancement process. Some noticed early worlds show up more created than anticipated, testing regular models that predict slower improvement. The revelation of an unimaginable mass of universes challenges the accepted distribution and game plan of enormous designs, uncovering a more complicated and denser enormous web than previously thought. These perceptions bring up entrancing issues and roads for additional investigation. The presence of enormous designs difficulties early models of vast construction arrangement, inciting scientists to refine models for a better clarification. Figuring out how such immense designs accumulated quickly after the Big Bang presents a riddle that requires a clarification that doesn't disregard key standards of cosmology. Huge differences in the states of the early universe, contrasted with expectations in view of existing models, have additionally been uncovered. These distinctions could propose beforehand obscure actual cycles, startling circumstances, or unidentifiable astronomical peculiarities. In straightforward terms, these varieties have incited researchers to re-examine and work on our models of the universe. Presently, there's nothing left but to say that further investigation is expected to integrate these amazing perceptions into a more extensive comprehension of the universe's beginning. Perceptions frequently give energizing, brief looks into the universe, yet in examinations, at times, they uncover contrasts. For instance, early perceptions might show explicit properties or arrangements inside far-off systems that, upon closer assessment, uncover vacillations in their piece structure or developmental pathways. In the end, huge peculiarities are extraordinarily intricate and require cautious examination for us to precisely grasp their real essence. Spectroscopy, a technique that unwinds the properties and history of divine objects, is a model. It includes examining the light transmitted or retained by cosmic particles. By analyzing the properties of the light, spectroscopy gives itemized data about the compound piece, temperature, thickness, and development of divine bodies. This examination assists us with grasping the starting points, advancement, and commitments of heavenly bodies to the inestimable embroidered artwork. The JWST has uncovered various cases where starting perceptions varied from later examinations. For example, starting perceptions of far-off cosmic systems recommended a straightforward construction, principally overwhelmed by lighter components like hydrogen and helium, in accordance with hypothetical assumptions. Anyway, spectroscopic examination utilizing the JWST showed entrancing varieties in basic marks, distinguishing heavier components or mixtures previously undetected or misjudged in the early universe. This challenges regular thoughts regarding the early universe's synthetic arrangement and the instruments liable for their turn of events and scattering across immense distances. Likewise, beginning suppositions about systems in the early universe were in view of starter perceptions proposing a moderately uniform example of improvement and association. Anyway, more point-by-point examinations by the JWST uncovered a substantially more different and complex exhibit of substance creations inside these worlds. The James Webb Space Telescope, JWST, keeps on reclassifying our comprehension of the universe by shedding light on recently stowed away corners of the universe. One of its generally thrilling capacities is its capacity to study exoplanets in uncommon detail. By investigating the airs of planets circling far-off stars, the JWST can identify critical compound marks, such as the presence of water vapor, carbon dioxide, methane, and other natural intensifiers. These discoveries give significant experiences into the potential livability of exoplanets and the conditions that could uphold life beyond Earth. As well as investigating far-off universes, the JWST is changing how we might interpret star development. It can notice the introduction of stars in areas where youthful stars are encircled by thick billows of gas and residue, which optical telescopes can't infiltrate. With its capacity to distinguish infrared light, the JWST catches the slightest glints of these new stars as they rise up out of the murkiness, offering a more clear picture of the cycles that lead to star and planetary framework development. By examining these districts, cosmologists are acquiring a more profound comprehension of how stars like our Sun appear and advance over the long haul. One more surprising part of the JWST research is its capacity to peer into the hearts of systems. Dark openings, especially really gigantic ones, are accepted to live at the focuses of most enormous universes. JWST's advanced instruments permit researchers to notice the way of behaving of issue around these dark openings, giving new bits of knowledge into their development, their effect on cosmic development, and the strong planes of energy they produce. These discoveries are assisting cosmologists with sorting out the story of how worlds and their focal dark openings advance together, affecting each other's development. Additionally, the JWST revelations are not just replying well-established questions, but also raising new ones. As it tests further into the history of the universe, it is uncovering peculiarities that challenge existing speculations and models. These difficulties drive mainstream researchers to rethink current cosmological models and open up new roads for research that were beforehand incomprehensible. The disclosures of the JWST are not simply pushing the limits of what we know, they're assisting with reshaping the major standards of how we view the actual universe.